In this lecture, we're going to talk about what are called the boundary layer simplifications. So these are the governing differential equations that we derived last time. So there were 4 of them. There was continuity, which is this top one. If I get my pointer to work here. So continuity, this we got from mass conservation. There was x momentum, which is a balancing of actual x momentum and then x directed forces, and here we have y momentum, and then this last one is conservation of energy. So you can see we have what are basically thermal terms here, and then we have this additional term which is related to viscous dissipation. So these are the equations in all their sort of glory, and what we'd like to do today is simplify them as much as we can for application in a boundary layer. So we talked quite a bit about boundary layers, and from a conceptual level, how they grow, at least for laminar boundary layers. And the practical outcome of that discussion was that boundary layers are diffusive, at least laminar boundary layers are, so they grow like the square root of alpha t, where time is the time that the fluid has been in contact with the plate. So time is, however long it takes to move from the leading edge to wherever you are, and the momentum boundary layer grows according to a similar equation, square root of nu, which is kinematic viscosity times time. So one of the things we did in lecture was take these equations and express them in terms of Reynolds number and Prandtl number. And so the outcome of that was here. We have that the momentum boundary layer thickness normalized by x, or the length of the plate, is proportional to 1 over the square root of the Reynolds number. And the thermal boundary layer thickness has the same proportionality, but there's also a Prandtl number in there. And so if you start looking at any realistic object and any realistic flow, you're going to find that 99.9% of the time the Reynolds number is pretty large. Certainly relative to 1, it's pretty large. And so the practical outcome of that is that the boundary layer thicknesses are always going to be a lot smaller than the size of the object. So if you want to think about it in terms of this particular picture, this thickness here, even though it's drawn as if it's pretty large, will actually be really, really small compared to this distance, which defines the size of the object. And so that's the basis of the boundary layer simplifications. Right? We're going to do the boundary layer simplifications by re-examining those differential equations, but now in the context of the fact that we expect the Reynolds number to be very large relative to 1, and therefore we expect that the boundary layer thickness will be quite a bit less than the characteristic length of the plate. And we're not going to differentiate between thermal and momentum boundary layers. For this particular analysis, we're going to assume basically that the Prandtl number is not too different than 1, so that those two boundary layer thicknesses are pretty close to one another. And we're going to just do what's basically called an order of magnitude analysis, keeping these things in mind. Right? We're going to do an order of magnitude analysis of each of the terms, with the hope that some of the terms will disappear, leaving us with a somewhat simpler set of equations to solve. So we'll do these in order. We'll start here with the momentum equation. With the continuity equation. So here's the continuity equation. I just rearranged it so that there's, the du dx term on one side and the dv dy term on the other side. And we're not trying to solve this equation. We're trying to estimate the order of magnitude of the different terms in it, right? So that's what this O means, right? So when I say O parentheses, I'm talking about what's the order of magnitude of the term inside of the parentheses, right? So this is basically telling me that whatever the order of magnitude of the du dx term is, that has to be the same as the order of magnitude of the dv dy term, right? There's only 2 terms. They have to have the same order of magnitude. So let's think about the order of magnitude of each of these terms in a boundary layer. Right? So here's a boundary layer, and we're thinking about, I guess to begin with, the du dx term, and then separately the dv dy term. So the du dx term is asking how rapidly does the x-directed velocity change as you move in the x direction, right? So the x-directed velocity can only change from u infinity, which is the free stream velocity, to 0, which is the velocity you'd have at the surface. And the distance over which that change can occur is related to the length of the plate, right? That's the x distance that changes occur. So with that in mind then, the order of magnitude of the du dx term is going to be u infinity, that's how much u can change, over L, that's how long it takes things to change in the x direction, right? So u infinity over L is what we'll use on this side. Then we come over to the right side and ask ourselves, well, what is the order of magnitude of dv dy, right? So how much can the y-directed velocity change, and then over what spatial extent will those changes occur? So the y-directed velocity at the plate is 0. The y-directed velocity here at the outer edge of the boundary layer is as big as it's going to get. I don't know what that is, but that's as large as it's going to get. We're going to call that v sub delta to indicate that that is the y-directed velocity out at y equals delta. So the changes in y-directed velocity must be about equal to v sub delta. What is the spatial extent over which that change can happen in the y direction? Well, delta, right? That's the distance from the surface of the plate to the outer edge of the boundary layer. So here I have the order of magnitude of dv dy must be v sub delta over delta. So this is the outcome of that analysis, right? I have two orders of magnitude, du dx, dv dy. I'll substitute them back up into the continuity equation, and it tells me that u infinity over L must be approximately equal to v sub delta over delta. So a couple things come from that that are kind of interesting. First of all, I can solve for v sub delta, and that's what I've done here. And what this equation basically tells me is that the y-directed velocity is quite a bit less than the free stream velocity, right? It's the free stream velocity multiplied by delta over L, and our whole premise here is that delta over L is really small, right? So not something you didn't know already, I suppose, right? We analyzed the laminar boundary layers by assuming that most of the transport was diffusive, and we didn't have a lot of y-directed velocity to help us out with energy and momentum transport, but this is sort of just confirming that, yeah, the y-directed velocity is small, and this is a pretty good scaling for how big that y-directed velocity can be. If we plug in our equation for delta over x or delta over L in terms of the Reynolds number here, then this is what we can use for the y-directed velocity. It's going to be the free stream velocity divided by the square root of the Reynolds number. So that's the useful things that come out of that. Anytime in the future now, as I go to these other equations and I have to scale the y-directed velocity, this is a good scaling to use. This is about how big it'll be, right? So I'm pretty much done with the continuity equation then. I've kind of used that as much as I can. We have 3 more equations to go. So let's move on then to the next one, which is the x momentum equation. So here's the x momentum equation. All I did to simplify it is got rid of the time derivative, so I'm assuming steady state. You can see I have my x momentum terms, and then over here the force term, so pressure force and those 2 viscous shear forces. So we'll break these apart into 5 different terms, 1, 2, 3, 4, 5. Again, I don't really care what the exact value of these terms are, but I'm interested in what the order of magnitude of each of these terms are. So we'll start from the left and move our way to the right. What's the order of magnitude of this first inertial term, this first momentum term? So I have rho, that's rho, and then I have u, so the order of magnitude of u is u infinity, and then du dx, which has order of magnitude u infinity over L. So that's what I've got here, rho u infinity squared over L. This is the order of magnitude of this first momentum term. Moving over to the right, this is the second momentum term. I have rho, then I have v, which is the y-directed velocity. So anytime I need to estimate the order of magnitude of v, I'm going to use that v delta, which I got from the continuity equation. And then du dy. So du dy has order of magnitude u infinity over dy has order of magnitude delta. So rho v delta u infinity over delta. This is the pressure gradient, so I have to estimate the order of magnitude of pressure pressure changes. So how much pressure changes should be related to how much the momentum of the fluid can change, and that's rho u infinity squared. So delta P is going to have order of magnitude rho u infinity squared, and then dx has magnitude L, right? So this is rho u infinity squared over L. Here's my two viscous terms. This is mu, and then I have d squared u dy squared. So I got to remember what this is. This is the second derivative, right? So this is the derivative of the derivative. So if I want to know the order of magnitude of du dy, that would just be u infinity over delta. And if I want to know the order of magnitude of the derivative of that derivative, then I would just divide that by another delta, right? So this is going to have order of magnitude u infinity over delta squared. And then we have this last term, which is the second derivative of u with respect to x. So same kind of thing here, right? I have mu, and then the derivative of u with respect to x would have order of magnitude u infinity over L. And if I want to take the derivative of that derivative with respect to x, that would be dividing it by another L, right? So this is going to have order of magnitude mu times u infinity over L squared. So I've gotten all these different terms. I've determined what their order of magnitudes are. It'd be nice to compare them to one another. So the first thing I'm going to do is introduce this scaling for v sub delta, right? So v sub delta is delta L over u infinity, right? So if I substitute that into here, the deltas cancel out, and I'm left with rho times u infinity squared over L. So these three terms, let me find my pointer. So these three terms, this guy, and this guy, they all have the same order of magnitude. They're all rho u infinity squared over L. So the real question is, how are these two terms related to these terms? Like, what's the size of these two terms as compared to the size of these terms? And so the way to find that out is to take this this equation or this set of orders of magnitude and divide them through by the order of magnitude of these inertial terms. So we're going to take this whole equation then, so all these orders of magnitude, and we'll divide through by rho u infinity squared over L. So right away you know I'm going to end up with one here, and one here. And then the real question is, what do I end up with here and here? And do I end up with something greater than or less than 1? So let's start with the second one. So that's this guy over here. So I'm going to take the order of magnitude of this second viscous term, which I said was mu times u infinity over L squared, and I'm going to divide by rho u infinity squared over L. So divide by rho u infinity squared over L. And if you look at this for a little bit, you can see that the u infinity on the top here cancels one of these guys on the bottom, and this L on the top cancels one of these guys on the bottom, and you're left with this, which is exactly equal to 1 over the Reynolds number. So remembering that the Reynolds number must be much greater than 1, that's one of the sort of principles of these boundary layer simplifications. That tells you that the magnitude of this term as compared to these other guys is pretty small, right? This is 1 over the Reynolds number, and we can neglect this in a boundary layer. In a boundary layer, this second term is going to be small because things change very slowly in X. Things change much more quickly in Y. All right, so that still leaves this term here, which we need to look at. So here I'm taking the order of magnitude of this first viscous term right here, and I'm going to divide by the order of magnitude of these inertial terms. So rho u infinity squared over L. So the order of magnitude of this first viscous term is mu times u infinity over delta squared. Right, I have y's in the bottom, so I get delta squared, and divided by rho u infinity squared over L. So if we multiply and divide this equation by L, then I'll get L squared over delta squared, and then I'll be left with rho u infinity L over mu. And this is 1 over the Reynolds number, so this is what I get right here. And this is a little confusing because the first part of this term would say, well, that's a very big, very important term because I know L is much bigger than delta. But the second part would say, well, this is actually really small because I know Reynolds number is much greater than 1. And actually, if you remember, our scaling is that a delta over L is proportional to 1 over the square root of the Reynolds number. What you find is that these two terms exactly cancel each other, and you're left with 1 here. So this first term actually must still be significant. It must be of the same order of magnitude as these other terms here. In fact, it has to be because that's kind of how the boundary layer evolves. So that's the outcome of this of this analysis, right? If we come back and look at where we started with this equation here, and by implementing the boundary layer simplifications, we were able to do two things that were important. The first thing is we were able to just get rid of this. In the boundary layer, things change really fast in y across the boundary layer thickness, but they change really slow in x, so along the boundary layer. And so this term will always be quite a bit smaller than this term. We can get rid of it. So our new simplified x momentum equation is this guy here. And the other thing we did that's actually pretty important is we said that all of these 4 terms that we retained, they all have the same order of magnitude, and that order of magnitude is rho u infinity squared over L. So we can keep this in mind to understand how big this equation is relative to the y momentum equation, which is what we're going to look at next.